So today we're going to be looking at something called L'Hôpital's rule. Now we're going to go back to the start of our experiences in calculus, and we're looking at limits. Now the idea of a limit is as we get arbitrarily close to a value, what does the output of a function or an expression become arbitrarily close to? Now early on we looked at algebraic techniques of working with limits. Now here we see things that are familiar, that are similar, or things that we've seen before. Here on the left, number 1, limit as x approaches 2 of x minus 2 over x squared minus 4. We might try direct substitution, and if we plug in 2, we get 2 minus 2, we get 0 over 2 squared minus 4 is 0. We have 0 minus 0 over 0. Well, what we did before was we looked at how do we factor this. This we could rewrite as the limit as x approaches 2 of x subtract 2 over the factors of the denominator are going to be x subtract 2, x plus 2. We've got a common factor that cancels out. We can say this is the limit as x approaches 2 of 1 over x plus 2, and that's going to give us 1 over 4. Limit solved. Another example, limit as x approaches 3 of x squared minus 2x. Well, direct substitution would give us 3 squared minus 2 times 3. Well, that's 9 minus 6. Okay, that equals 3. Direct substitution works fine when we've got something like that, a polynomial. We saw something similar to this where we know that the limit as x approaches 0 of sine of x over x is going to be 1. This is very close to that. What I could do is a little bit of manipulation. Turn this into limit as x approaches 0. I'm going to multiply top and bottom by 5 halves. That'll become apparent in a moment. I'm going to multiply by 5 halves for 2x. That's going to turn this into limit as x approaches 0. That's going to be 5 halves sine of 5x over, well, 5 halves times 2x is 5x. Well, that sine of something over that same something is just 1. That is the worst one ever. 1. So the whole thing is equal to 5 over 2, which you can see back in those coefficients. Now we kind of just accepted that this notion of sine of x over x is 1. We looked at the graph, we looked at a table of values, and kind of said, yep, that's it. Limit as x approaches infinity of e to the 2x over x squared e to the x. Well, I can rewrite this as limit as x approaches infinity of, well, e to the 2x over e to the x is e to the x over x squared. Now, we argued before that e to the x, this is going to be kind of a big infinity over infinity, so bigger infinity divided by a smaller infinity is going to be infinity. And that's just a little bit unsettling, thinking which one gets bigger faster, which one grows faster. We don't really have a metric for kind of saying otherwise, other than just saying e to the x is faster than x squared. We're going to fix all that. In these cases, this one, we have infinity divided by infinity. If we direct substitute into sine of 5x over 2x, we have 0 divided by 0. Back to the start, albeit an easier limit, we direct substitute with 0 divided by 0. All three of these are known as indeterminate forms. Indeterminate form is something of the case 0 divided by 0, infinity divided by infinity, infinity multiplied by 0, and indeterminate, the idea is, what is it? We know that 0 divided by anything is 0, but anything divided by 0 is undefined, but anything divided by itself is 1, but 0 times anything is 0, but infinity times anything is infinity. What's really happening here? What happens when we do infinity subtract infinity? Might be infinity, might be 1, might be 0. How about 1 to the infinity power, or 0 to the 0 power, or infinity to the 0 power, or 0 to the infinity power? All of these are known as indeterminate forms. And so how do we manage these when we're talking about limits? That's where our good buddy L'Hôpital is going to come in. Now before, we are factoring or we're looking for things or kind of reasoning. Here, limit as x approaches 1 of natural log of x over x minus 1. Well, there are no factors. If we direct substitute, we're going to have natural log of 1 is 0 over 0. There's nothing to factor. It is, again, one of these indeterminate forms. So what can we do about that? Enter L'Hôpital's rule. The idea behind L'Hôpital's rule, if we have the limit as x approaches a, now this might be 0, this might be infinity, this could be any specific value, of some rational expression, f of x over g of x. L'Hôpital's rule says that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x whenever we have an indeterminate form. That is the worst whenever. Whenever f of x over g of x is indeterminate form. has to work out that we have 0 divided by 0, infinity divided by infinity, infinity times 0, infinity subtract infinity, or one of those exponents, those power statements. If we have one of those statements, then L'Hôpital's rule apply, where we take the derivative of the numerator divided by the derivative of the denominator. Now, as a proof, let's take this. We're going to have a differentiable function where g prime of x is not equal to 0. Now, this can work when we have our limits equal infinity or equal 0, and one of these indeterminate forms. As a proof, let's start off saying that we have two differentiable functions, and we're going to look at the derivative or limit as x approaches a of f prime of x over g prime of x. Now, direct substitution, that would be that this is f prime of a divided by g prime of a. By the definition of derivative going back, f prime of a is the limit as x approaches a of f of x subtract f of a over x minus a over limit as x approaches a of g of x minus g of a. That's an a all over x subtract a. That's the definition of the derivative. Well, we see that there's that x minus a factor in both. So this is the limit x approaches a of f of x subtract f of a over the limit as x approaches a of g of x subtract g of a. And we've fallen into this because f of a is 0 and g of a is 0. The limit is x approaches a of f of x minus 0 over the limit as x approaches a of g of x minus 0. That's because each of those are 0. We have an indeterminate form. And that simply is limit of f of x over, as x approaches a of f of x over g of x. There's our connector. So L'Hôpital's rule, if we have an indeterminate form, that must happen first. One of those indeterminate forms, then the limit of the quotient is the limit of the derivatives, of the quotient of the derivatives. So the derivative of the top, the derivative of the bottom. Let's actually see this in action now. I'm going to go back to this one where we could not factor it. We have these indeterminate form type 1, where we've got 0 divided by 0. We had the limit as x approaches 1 of ln of x over x minus 1. Direct sub would be ln of 1 is 0, 1 minus 1 is 0. All right, checks out. L'Hôpital's rule says that then we can take the derivative of the top, the derivative of the bottom. So we've got the limit as x approaches 1. Keep using your appropriate limit notation. The derivative of natural log of x is 1 over x. Derivative of x minus 1 is 1. So this is equal to the limit as x approaches 1 of 1 over x, which is nicely just 1. So there's that sine x over x. Applying L'Hôpital's rule, direct substitution would give us 0 over 0. Oh, okay. That's going to turn into now, applying L'Hôpital's rule, limit as x approaches 0, derivative of the top, derivative of sine is cosine over derivative of the bottom, derivative of x is 1. Ooh, no more 0 divided by 0. Limit as x approaches 0 cosine is cosine of 0 is 1. Much simpler explanation now that we've got L'Hôpital's rule to help us out. Next up, we've got this monster. Well, if we direct substitute, we're going to have the square root of 1 minus 1 minus, so that is 1 minus 1 minus 0 over 2, so that's 0, all over 0 squared. Okay, so the whole thing is 0 over 0. L'Hôpital's rule. We're going to take the limits as x approaches 0. Now, derivative of the top is 1 over 2 square root 1 plus x minus 1/2 all over 2x. So now that we've applied L'Hôpital's rule, direct substitute, and we've got 1 over 2 square root 1, so that's just 1. So that's, 1/2 subtract 1/2 is still 0 over 0. Oh, 0 over 0. We'll apply L'Hôpital's rule a second time. I'm going to take this as being 1/2, 1 plus x to the negative 1/2. So when we apply L'Hôpital's rule a second time, limit as x approaches 0, that is negative 1/4, 1 plus x to the negative 3/2 all over 2. We're dividing by 0. Direct substitution, that whole thing is 1. The 1 to the negative 3/2 is 1. We have negative 1/8. Happy days. Let's look at the second indeterminate form type. This time, infinity divided by infinity. Now, infinity divided by infinity is really like 1 over 0 over 1 over 0, which then is 0 over 0. So it's an equivalent indeterminate type. Limit as x approaches pi over 2 of secant x over 1 plus tan x. If x approaches pi over 2, remember that is 1 over cosine. So pi over 2, that would be 1 over 0. Ooh, that's infinity. Tangent to pi over 2, that's sine of pi over 2 over cosine pi over 2. So that would be, again, infinity. L'Hôpital's rule applies. We'll take the derivative of the numerator, take the derivative of the denominator. So we've got limit as x approaches pi over 2. Derivative of secant is secant tangent over derivative of 1 is 0. Tan x is secant squared of x. This is, we've got the limit as x approaches pi over 2 of tan x over secant x, because I canceled one of those secants. I'm going to rewrite this. This is sine x over cos x over 1 over cos x. So over cos x cancels. We have the limit as x approaches pi over 2 of just sine x and 1. Limit as x approaches infinity of natural log of x over 2 root x. Direct substitution, natural log of infinity, well, that's going to be infinity. 2 times the square root of infinity. Well, square root of infinity is infinity. We've got an indeterminate form. So, applying L'Hôpital's rule, got 1 over x. Let me make certain that I use my correct limit notation. Limit as x approaches infinity. We've got 1 over x over, that is 1 over 2, so 1 over square root of x. And simplifying or rewriting that, limit as x approaches infinity, that is 1 over square root of x, which is then 1 divided by infinity. 1 over infinity goes to 0. Next indeterminate form, type 3, we have infinity times 0. Well, infinity times anything is infinity, but 0 times anything is 0. What is it? I'm going to take this and turn it into something that we've already seen. So direct substitution, we'd have infinity times sine of 1 over infinity. That's going to be infinity times sine of 0, and that's going to be infinity times 0. L'Hôpital's rule applies. I'm going to rewrite this. Limit as x approaches infinity of sine of 1 over x over 1 over x. X, I can rewrite as over 1 over x. It's about to multiply by the reciprocal. Now, this is 0, this is 0. Our original indeterminate form. Derivative of the top divided by the derivative of the bottom. So apply L'Hôpital's rule. Limit as x approaches infinity. Now this is sine of x to the negative 1. It's going to be negative x to the negative 2 cosine x to the negative 1 all over negative x to the negative 2. Ooh, take a look at that. Common factor. We've got limit as x approaches infinity, cosine 1 over x. That goes to 0. Cosine of 0 goes to 1. Turn it into something that we were used to seeing. Next example, limit as x approaches 0 from the right, and that from the right is necessary because the domain of ln of x is 0 to infinity, excluding 0, so only to the right. If we plug in a 0, well, that's 0, and that's negative infinity, which is equivalent to 0 times infinity. I'm going to rewrite this as limit as x approaches 0 from the right of natural log of x over 1 over x. L'Hôpital's rule apply because this is now negative infinity divided by infinity. We've got one of our indeterminate forms. So L'Hôpital's rule, limit as x approaches 0 from the right, this is 1 over x over negative 1 over x squared, giving us limit as x approaches 0 from the right of negative x, giving us 0. Next type, infinity to minus infinity. Oh no, oh, which one's bigger? Are they comparable? Here we've got 1 over the natural log of x, so 1 over the natural log of 1 would be 1 over 0, that's infinity. 1 over that would be infinity, subtract infinity. In this case, let's get a common denominator. This is limit as x approaches 1. Common denominator, we'll turn this into x subtract 1, subtract natural log of x, all over natural log of x times x subtract 1. If we check, plugging in 1, we have 0 divided by 0. We've turned it into indeterminate form number 1. Derivative of the top over the derivative of the bottom. So we've got limit as x approaches 1, that is 1 subtract 1 over x, over product rule, that is x minus 1 over x plus, what do I do there, ln of x. neatening things up, I'm going to manipulate this. I'm going to multiply by x over x. Multiplying by x over x turns this into limit as x approaches 1 of x subtract 1 over x subtract 1 plus x natural log of x. We do see that when we plug in 1 direct substitution, we have 0 over 0 again. Apply L'Hôpital's rule a second time. So I'm going to rewrite. We've got limit as x approaches 1 of x subtract 1 over x subtract 1 plus x natural log of x. Applying L'Hôpital's rule another time, with the limit as x approaches 1, derivative of the top is 1, derivative of the bottom is 1 plus product rule. I'm going to have natural log of x plus x over x. Now, direct substitution, we have 1 over 1 plus 0 plus 1. We get 1 half. Ooh, not too shabby. Next up, limit as x approaches infinity of e to the x subtract x. Well, that's going to clearly be infinity subtract infinity, but we don't exactly have common denominators. I'm going to manipulate this and turn this into, so limit as x approaches infinity of factor x. That's going to leave us with e to the x over x subtract 1. Now, as x approaches infinity, this is going to be infinity. And, well, this statement is infinity over infinity. Let's evaluate that by itself. So the limit as x approaches infinity of e to the x over x, we can apply L'Hôpital's rule. That's limit as x approaches infinity of e to the x over 1. Ooh, that gives us infinity. So this really gives us infinity multiplied by infinity minus 1. All right, infinity multiplied by infinity is infinity. Now we look at our exponential, our power indeterminate forms. First off, we have 1 plus 1 over x raised to the x. You may remember this as the definition of e from past experiences. Well, we're taking the limit, really, of this equation, y equals 1 plus 1 over x to the x. So what we're going to do is, back when we could not take a derivative, we're going to take the log of both sides. So I'm going to take the natural log, and remember, properties of natural log, this turns into x ln 1 plus 1 over x. Now, I'm taking the net limit of this. I'm going to rewrite this as the limit as x approaches infinity of x natural log 1 plus 1 over x. If we substitute in, that's going to be infinity, that's going to be 0, so natural log of 1 is, that's infinity times 0. Infinity times 0, we can work with that. So this is going to become the limit as x approaches infinity of natural log of 1 plus 1 over x over 1 over x. That, now we can apply L'Hôpital's rule. I've got the limit as x approaches infinity. This is 1 over 1 plus 1 over x. That's going to be multiplied chain rule by negative x to the negative 2 over negative x to the negative 2. That's out. Now when we apply direct substitution, this is 1 over 1 plus 1 over infinity. That's 1 over 1 plus 0, 1 over 1. That gives us just 1. But that's the limit of the natural log of y. So that's telling us that ln of y, natural log of y, is equal to 1, which then gives us that y is equal to e. Y is the limit that we initially wanted. Let's try the next one. Limit as x approaches 0 from the right of x to the x. Well, that's going to give us 0 to the 0 power. Yikes. I'm going to take the same strategy. Regarding this as x to the x is y, I'm going to take the natural log of both sides. That'll be x natural log of x. Now, I do realize I'm skipping a step in there, pulling the exponent out. Let's reconsider this as limit as x approaches 0 from the right of x natural log x. Direct substitution, that is 0 times infinity. That's 0 times infinity. We actually already saw that. This is approaching 0. That was an earlier example. So we have natural log of y. It's giving 0. So y is e to the 0 is just 1. Next one here. We take this, infinity raised to x raised to 1 over x. It's going to be infinity to the 1 over infinity, which is infinity to the 0. I'm going to use this same strategy. Y is equal to x 1 over x. So taking the natural log of both sides, we've got 1 over x natural log of x, so I can apply L'Hopital's rule. We've got limit as x approaches infinity of 1 over x times the natural log of x. Now that's going to be 0 times infinity. So I'm going to rewrite this as limit as x approaches infinity of, well, this is an easy one, ln of x over x. That's infinity over infinity. Derivative of the top, derivative of the bottom. We've got limit as x approaches infinity. That's 1 over x over 1. So that 1, who cares? 1 over infinity gives us 0. Different examples with L'Hopital's rule. The whole thing going back to the start. Whenever we have one of these indeterminate forms for our limits, we can make it look like 0 over 0, infinity over infinity. And in that case, that limit becomes, we can take the derivative of the top divided by the derivative of the bottom. Good luck. Try it out. Let me know if you got any questions.